I'm really excited to be here today telling you about some of our recent work that we've done on computational single photon imaging. But let me start with a question to the audience. How many of you know what these photographs are? A few? Okay, so I'm actually surprised because this is the horse in motion. It was a big bet between Leland Stanford and the experimental photographer Edward Muybridge back more than 150 years ago, where it wasn't clear if there was ever any gait of the horse where all 4 feet are up in the air at the same time. So Edward Muybridge set out to develop an experimental camera system that looked kind of like this, where the horse would trigger different mechanical shutters set in front of these cameras on the side, and they would trigger these mechanical shutters, they fall down, and it basically creates a high-speed camera back in the day with photoemulsion on glass plates and things like that. So you've probably seen the movie The Matrix with the bullet time effect. That is a modern implementation of exactly this technique that is from 1870-something. So the argument I'm trying to make is that imaging is one of the oldest disciplines at Stanford and has been around since before it's actually been a university. And today we carry on, in the spirit of Edward Muybridge, work on digital imaging, in particular computational imaging. So what's computational imaging? It is this co-design of optics, sensing, and the algorithms that process the data to enable new kind of imaging modalities. The same kind of paradigm also applies to computational displays, also where we co-develop and co-design electronics, optics, and algorithms while exploiting the limitations of human vision to deliver new kinds of experiences. So let me give you a couple of examples. Computational imaging has been around for maybe 10, 20 years now, and some examples include high dynamic range imaging. That's something that you've implemented on your cell phones today. Every time you press the shutter button, the camera actually takes multiple pictures with different exposure times, each exposure time potentially not being able to capture the full dynamic range or contrast of the scene. So if you have very dark parts of the scene in the same picture as very bright parts like the sun, then none of these can be well exposed at the same time. So high dynamic range imaging will compute a single image from multiple exposures. And similar techniques apply to super resolution that you may know from CSI, Miami, or other crime series on television. And then light field imaging, of course, is also something that was developed here at Stanford. On the display side, very similar concepts apply. High dynamic range displays have now been around for about 10 years, and whether you know it or not, most televisions you buy at Best Buy today have some variant of this technology integrated, and super resolution light field display are also active areas of research that are making their way into consumer electronics. So today I'd like to focus on bringing these two together, computational cameras and computational displays, and I'm going to call that computational light transport. So the idea is that we're going to use some kind of a display or a projector or some kind of a structured light source to probe information from the physical world that we can then record with the camera. And that may sound a little bit abstract, but a couple of intuitive examples include LiDAR systems, so active 3D imaging systems where you send a pulse of light into the scene, you kind of timestamp the returning photons, and with that technique you can build up a 3D image of your environment to help make more robust decisions, for example, in autonomous driving. Another example includes 3D imaging on smartphones. For example, the iPhone X has a miniature version basically of the Microsoft Kinect inside, and they use it for 3D facial authentication for your phone. These kinds of techniques have a lot of applications in augmented reality and virtual reality, scanning your environment, being able to track a person, your hands, or simply digitizing your living room to put virtual furniture in is something that's kind of really important in these emerging AR/VR systems. So let's talk about more about direct time-of-flight 3D imaging or active 3D imaging. So you can think about this more like long-range LiDAR types of systems. So it's pretty straightforward. We have usually a picosecond laser or nanosecond laser that sends a pulse of light into the scene. There's a very sensitive detector. I mean, we only get a few photons back for long-range applications. So typically we use single-photon detectors like single-photon avalanche diodes or SPATs. And then we're going to scan that over the scene, or we have an array of these laser detector pairs, and that gives us 3D image. So the challenges here are light efficiency, because that determines what the range is. You can't just arbitrarily crank up the light power because of eye safety constraints. So we need to be very efficient on the detector side, for example. But we also need to do high-speed timestamping simply because we want to have a precise depth map, because it does matter how precise your depth map is to be able to make robust decisions. So the solution for that, or an emerging solution for that, includes time-correlated single photon counting. And the way that works is, again, you have a laser that sends a short pulse into the scene. Typically, we just measure the direct reflections, which doesn't really change the pulse shape of the light source. But there's a lot of light bouncing around between different objects. Light may be refracted or reflected from various objects. I mean, think about a car. It's pretty specular. The paint is actually very shiny, so light bounces around in the scene, and that can change the temporal characteristics of this laser pulse. The SPAT detector will actually digitize the returning waveform and assign timestamps to these photon events. And it'll, over time, build up a histogram that tells you the temporal distribution of the returning photons by counting these photons in different time bits. If you use an array of these detectors, of course, you can do that simultaneously for multiple pixels, basically. This technology isn't quite as well developed as CMOS imagers today, so we have arrays of maybe 256 diodes, not so much 20 megapixel sensors yet, but they all collect the spatiotemporal information. And that's great for LiDAR, but it's also potentially useful for other computer vision and imaging applications. And I'll show you some examples of an experimental SPAT system that we built in the lab. So in this case, we have a simple glowing fiber. It's just an optical fiber. So you send light in on one end, it comes out on the other end, but along the way, a couple of these photons will actually scatter out on the side. We couple a laser on it on the side here. It sends pulses of light at a certain repetition rate into the scene, and then using our system, we can basically capture how these light pulses propagate in the scene. So in some sense, we have a camera that can record light at the speed of light. Right? If you haven't seen these videos before, it's actually quite impressive because we can really resolve light transport at this picosecond time scale, which corresponds to only a few centimeters of propagation speed at the speed of light. And we call that transient imaging. So what you see here is you see one laser pulse coming in from the left. It rotates around a couple of times. We rolled up the fiber to extend the path length a little bit. And then after it rotated around a couple of times on the right, it actually diffuses out into the scene at the very end. And you see multiple laser pulses coming in because the laser operates at a certain repetition rate. So that's really wonderful. And the way we did this is actually we basically just hacked the firmware of a LiDAR system, right? Any LiDAR system captures this kind of information. In this case, we have a 1D array of these single photon diodes, 256 of them. We scan them horizontally over the scene, each time capturing a temporal histogram, and that builds up this 3D spatiotemporal volume, which we call a transient image, and then we just play back that transient image, which you can see on the left here. So this is really fascinating and interesting. Our research aspects are more on the signal processing, on the optimization of making decisions under the uncertainty given by these image formation models. We deal with Poisson noise, priors, and so on. I'm going to skip over the mathematical details, but that's kind of what we do in the lab and what we publish our papers on. But some of the results that we've been able to capture include, for example, here is a bottle of murky water. So you can think about this as a representation for scattering media or participating media. Think about a self-driving car driving through fog. It's a little bit challenging to get robust depth information in harsh weather conditions. So being able to capture light transport at this resolution can really enable new kinds of applications and more robust decision making. So on the right, you can see the output of this video. It's a little bit lower resolution than the high resolution camera image that we captured on the left. And what you see is that there's this laser pulse going into the bottle. It's a little bit scattering, so light scatters all over the place. There's a cap in the bottle where light bounces around a couple of times, and then some of the light actually gets reflected all the way back here because light bounces around in the cap and then comes back over here. So we can now capture light at a speed that is unprecedented in the world of imaging, and that we've been able to only simulate in the world of computer graphics and computer vision before. How could this help, for example, with detecting objects or classifying objects? Well, if you have ambiguous scenes like this one, where a statue is actually reflected in the mirror, and you see both of these, we could, take a look at this transient video on the right, where we see this wavefront propagating through the scene, and we can see the reflection of the statue at a later time than the actual statue itself, so we can disambiguate them based on this time-of-flight information. So in this case, the laser pulse comes in from the right, goes through a diffuser, and you can think about the shell of light propagating through the scene, and you only see the intersection of the shell and the background and the reflections of these scene objects. All right, so this is a fundamental technology that makes constant progress. We really contribute on the signal processing side of these imaging systems, and these are, really cool to look at, but also useful for depth estimation, for separating the direct light transport from the global light transport, for analyzing this kind of a light transport, and they may eventually enable fundamentally new imaging modalities for image processing computer vision. And so that's ongoing work in the lab. I want to focus on one particular application for the next 10 minutes or so, and that's non-line-of-sight imaging. So non-line-of-sight imaging is this idea that was introduced by Ramesh Raskar at MIT about, maybe 6-7 years ago. And the idea is really this. If we have a camera with an active light source on the right and a person or some kind of an object inside a room or hidden from the direct view of this camera, is it possible to recover the shape of this object? And it may be if we use this pulse light source on the camera that sends a pulse of light into a visible part of the scene, for example, in this case, the door. Some of the photons will scatter behind the corner, interact with the hidden scene that the camera doesn't see directly. Some of these photons will come back to the door, and then some of these will go back to the camera. So this is a 3-bounce problem, where we have a bounce from the laser to the door, to the person, back to the door, and then to the camera. And so the question is, from this time-resolved light transport that we just saw, is it possible to robustly recover the shape and reflectance of the scene that is outside the outside the line of sight of the camera? And although we illustrate that with a couple of toy examples now, this could really help, for example, self-driving cars again to make decisions well ahead before the cameras or other sensors actually see the objects or another car or a person that is hidden from the direct line of sight. So here are some of our recent experiments. Again, the idea is we use a light source on the left, is the laser, the spat detector. We scan it over the scene. In this case, it's kind of a very simple scene because we have a wall in the background that we see. Then there's an occluder, which prevents us from seeing the bunny directly. And then the bunny is hidden behind the corner, and we have to analyze the indirect reflections that went to the wall, to the bunny, and then back to the wall. So here's an actual experimental measurement, trying to convince you that we have enough sensitivity in the sensor to actually detect this indirect light transport. I mean, the direct light transport really dominates this image formation model, and this is a logarithmic scale on the plot up here, so we get like hundreds or thousands of photons coming back from the direct reflections, but we only get a handful of photons coming back from these indirect reflections because the light simply scatters all over the place. So it's actually very surprising that we see anything at all. But we see this little bump, and that is maybe at a certain time, in this case about 4 nanoseconds after the direct reflections, which corresponds to a path length of about 60 centimeters. So we know from physics that there's something there about 60 centimeters away from that patch, but we don't know where it is. It could be anywhere along this arc. So there's no way of directly recovering the shape of this bunny. So now what we're going to do is we're going to scan a rectangle on this wall, and that is a transient image again, just like the ones I've shown you earlier, except there's nothing exciting going on. It's just a wall, a white wall. But from these indirect reflections, we then potentially can recover the shape of these objects. So I'll show you a couple of equations. You don't need to understand them necessarily, but the basic idea is that we start out with these time-resolved measurements from our spat detector. It's a spatial temporal distribution of photon counts, and what we want to recover is this three-dimensional shape of the hidden object, in this case the bunny. And then we have a couple of constraints based on the time of flight and radiometric fall-off that we need to take into consideration. So you can discretize this and it becomes a linear inverse system. All of you probably remember that. We basically solve an equation system B equals A times X, but for a very large system. We have so many different unknowns in this volume that it becomes actually pretty infeasible to directly work with linear algebra on this system. So just to give you a sense, if we have a volume of 100 by 100 by 100 voxels for the bunny, the matrix has 1 trillion elements. If we go to higher resolutions, where we have 1,000 cubed voxels for the hidden volume, then we would need 9 petabytes of memory to just store this matrix as a sparse matrix, right? It's not dense, but it's sparse, but yet we need a lot of memory. So to overcome that, people have in the past looked at, tricks like backpropagation or iterative inverse methods that aren't really practical because they take tens of hours or even days to process. So what I'm going to try to convince you is that we can actually do all of that potentially in real time with practical detectors and lasers that are already being used by LiDAR systems today. So the challenges of non-line-of-sight imaging include we need light-efficient, high-speed timestamping and this light efficiency. We need efficient scanning methods, and we need to be able to somehow process this data in a very efficient way to solve the inverse problems well. So before I dive into the details, I'll show you an example of one of the scenes that we actually recorded with our system. So this will be the actual measurements. So these are photon counts, the transient image of the wall, which include only these indirect reflections. So what you can see is this wave-like pattern. This is actually a propagation kernel of light in free space for individual points. It propagates in these conical surfaces, and I'll tell you more about this in a second. But then, with less than a second of computation time, we get back the shape of this object, which is given much lower resolution than a high-resolution camera image, but we can actually robustly recover and estimate the shape of this object, even when it's hidden from the direct line of sight. So to solve this light efficiency problem and the high-speed timestamping, we're just going to use these spats I told you earlier about. And these are compatible with existing LiDARs. They are low-cost fabrication. We can now do that in potentially in CMOS, in silicon, at least for visible light, or maybe in gas, and there's increasing availability of these types of sensors. For the scanning method, I haven't actually told you how previously people scanned these kinds of scenes, but we developed probably the easiest and the most intuitive scanning method, which is simply to scan this, detector laser pair over the wall in a confocal setting, which means that the laser probes the wall at one point and the detector only records at that point as well. So that's pretty much what every LiDAR does already. But people in the world of non-line-of-sight imaging haven't done that before. So here's our prototype. It's pretty straightforward. We have the single photon avalanche diode here on the right, focusing lens. We have a picosecond laser coupled into this with a beam splitter, so they're coaxial. And then we have a galvo system that allows us to scan the laser beam vertically and horizontally over the scene. So we emit a pulse into the scene and measure the returning photons with the detector. So it's pretty straightforward. The key is really on the signal processing and the inverse methods in this case, because there's no way we can infer the 3D shape of the object directly from the measurements. There is this inverse problem in between. So to help you understand kind of how we approach this, I want to do it in 2D first, because it's a little bit more intuitive. So think about the hidden space as a 2D space where we have X and Z. So Z is away from the wall and X is actually directly on the wall. So we take these measurements, these time-resolved measurements, only at some parts of the space that are accessible, that are directly visible. So anything in this red square is not directly visible to the camera, but we can probe it at specific points, basically at the wall, and we get this temporal information. So I'm kind of like linking space and time in this little diagram. So if we have a point that is hidden in that volume, and it either reflects a pulsed light source or it emits a little pulsed light source, that propagates in space-time actually using what's known as a hypercone. So it propagates with a certain speed in all directions isotropically, and over time you can plot this reflection as a cone. And this cone is known as a hypercone. Actually, this is a common tool in relativity. There it's known as Minkowski's light cone. If you have an event in space-time, it can only affect other events within this cone because it cannot propagate faster than the speed of light outside this cone. So it's the same kind of an idea. And if we have multiple points in this hidden volume, the image formation model is actually, we can model it as a convolution between this hypercone and these individual points. So now again, we're taking these measurements only at a subset of the space, and that's basically an intersection of this spatiotemporal slice with these light cones, these are our measurements. So we don't know where the points are, but we can measure these trajectories, which are the intersections of the hypercone with this plane. And this is laterally shift invariant, but not depth invariant. So you can see that as we intersect the cone at different depths, we get different amounts of curvatures of this hyperbola. So that makes it difficult to invert. So here are some actual real-world measurements, and you can clearly see these intersections with the cone. This is just a 1D measurement along the line. These 3D measurements I showed you earlier generalize that to higher dimensions. So in this case, we're looking at a 3-dimensional intersection of a 4-dimensional space-time hypercone. And it may take a while to wrap your head around it, but this is basically a slice through a 4D hypercone. Okay. So I'll keep the math light. Again, this idea of confocalizing the measurements or putting them coaxial allows us to change the image formation a little bit. And basically, in that image formation model, we now have our hypercone as the propagation operator, and that makes it really nice. The 1/r square form, 1/r4 term here can be pulled out of the integral. We do some change of variables. That's actually the secret sauce, but I don't have enough time to really go into the details here. Basic idea is that we can model this image formation model as a 3D convolution. And compared to the matrix vector multiplication, we can now work with significantly less memory. We can do convolutions very efficiently. Neural networks use convolutions all the time. And we can, in fact, find a closed form inverse solution that we can compute in real time by inverting this convolution in the Fourier domain in a computationally and memory efficient way. So the basic idea is we take our 3D measurements of these transient images. We perform the change of variables. It's a little transform. We do an inverse filter by dividing through the 3D optical transfer function of this hypercone, and then we get our bunny back at the end. And we can do all of that very efficiently in hardware. So here's some results we got outdoors. So these are the first results that were captured outdoors with this non-line-of-sight imaging. We have a cardboard of the shape of an S for Stanford at about a meter and a bit away from the wall. There's indirect sunlight actually contaminating these measurements. Here's the scene from the perspective of the detector and the laser. So we really only see that wall. We don't see the shape at all. And then we're going to scan the laser point over the scene. It's actually so faint that you probably won't be able to see it. It's scanning somewhere over here. I don't know if it's visible on the projector, but it's basically scanning point by point over the scene here. But there's so much ambient light that makes it especially challenging. So here are the measurements we got in about a minute or so. We scanned over the scene. We can still see the structure of the wall, but we have some of this time-resolved light transport information in there, and we can run it through our closed-form solution, which is very fast, and then recover a rough estimate of the shape. So in this case, as I said, the measurements are actually heavily polluted by ambient light from the sunlight, and that contributes to some of the noise that you see in the reconstructions. But you can clearly make out the shape of this. I'll show you a couple more examples. So this is the mannequin result that I showed you earlier already. We actually painted it in white so that it would reflect a little bit more light because it's just so challenging to see any of these photons at all. So these are the measurements again. You can see these intersection of the hypercone. We then process that data very quickly to get the 3D shape of the object back. And these are pretty much the state-of-the-art results for non-line-of-sight imaging. There's a big DARPA program going on this with about 100 PIs working on it, and I think we really made a significant step forward in that program here with these results. So it's a big challenge for imaging systems to really make the invisible visible. In this case, it's a traffic sign. Traffic signs are oftentimes retroreflective to reflect a lot of light back to the driver. So these special types of material properties can be exploited also in this algorithm because they also reflect more light back to the wall. So it's actually much easier to work with retroreflective objects, for example, these traffic signs or safety apparel, than it is to work with regular diffuse objects. There's a bit of occlusion also between two characters, so the algorithm handles that reasonably robustly. Okay, and this is a diffuse object where we have a lot of ambient light. So again, the ambient light would then negatively affect the image formation model because we don't really model it all that well. But still, we're doing much better. And we can induce priors and more sophisticated optimization schemes, which will take a longer time, but actually work much better and suppress this noise. That just doesn't work in real time. Okay, so here are some recent results from the lab. That wasn't really published yet. But we kind of try to push it to the extreme, and we can actually do all of that in real time now. We have a pretty low power laser, so we don't actually get too many photons. In this case, the object is just 2 bars of retroreflective material that you see on the left. It's hidden from the direct view of the camera. We're just rotating the target, moving it back and forth, and you can see the video captured in real time. So in this case, the exposure time is very short. We only get maybe 1 photon or 2 photons per measurement, but still the algorithm is robust enough to be able to detect the object hidden from the line of sight. And so this may be actually something that's practical earlier than you may think. So going back to this idea of 3D imaging, that's something that's being used pretty much everywhere in autonomous driving, in remote sensing, but also for entertainment. You know, there are many different implementations of 3D cameras or active 3D cameras. For example, LiDAR systems, you know, research on SPAD-based LiDAR systems have now demonstrated last year up to a range of 10 kilometers or so. So it's really impressive how much progress we've been making in this community. And we have other types of 3D imaging systems as well. But the range, acquisition speed, and resolutions are fundamentally limited by the number of photons that you can emit into the scene and then detect, of course, by the detector. So if there are no photons, you can't do anything. And so one idea that we had last year was, why not use sensor fusion? Because we have so many different other types of sensors on the car. For example, regular cameras. Why not capture a noisy point cloud with these LiDAR systems, which you can see on the left, and somehow utilize the information that's included in conventional images, because those are high resolution. We have a lot of structure of the scene in there already. It's just, you know, they're complementary in some sense, because the LiDAR data is low resolution, it's noisy, but it has the 3D information, but the 2D image has pretty much everything else. So over the last couple of months, we've been working a lot on sensor fusion between intensity images and the SPAD data, and the basic idea is, you know, you scan fast 3D point cloud like this. Normally, you would have to do depth estimation on this, but we combine the intensity image that we have at the same time. And like pretty much everybody else, we're using deep learning for this. So we build a multi-scale network to process the raw 3D point clouds to get an estimated depth map. We're also taking the intensity image into account. So we train this network in a pre-processing step, and then we can run it at a very fast rate after the fact. We can also use the depth image to do super resolution, so we can try to upsample the depth map to get not only, you know, more robust depth information, but also at a high resolution. And again, we cannot need access to the raw photon counts, and that's not something that we can do with commercial LiDAR systems, because the manufacturers typically don't give us access to the raw data, so we need to build our own systems. And here's a scanning-based system that we built. So in this case, we have a blue laser. There's a scene. Right now, it's scanning at 20 hertz with the lights on. The laser is actually so weak that you don't see it at all. If we just turn the lights off, you can actually see the laser. It scans at 20 hertz. And now you can actually see the active illumination. And again, these are pulses of light that are run at a repetition rate of about 1 megahertz or so. So here's my student captured it with a cell phone at 240 frames per second, so you can actually see the LiDAR system basically scanning over the scene at a pretty fast rate. And here's the kind of data that comes out of the SPAD measurements. It's a very noisy point cloud. There's ambient light. There's actually a lot of defects in the SPADs too. We got this one from a colleague of ours as a research unit, and then with our processing algorithms with these neural networks that are all shown in the bottom, we can significantly outperform what the state of the art is in signal processing for LiDAR depth estimation, such as log match filtering. And Shin et al. Was a Nature Communications paper just published 2 years ago. So in all variants, our networks outperform that state of the art. And we can try to do this guided upsampling as well to get super resolution. So when you have a lot of ambient light, you can see that this super photon counts is actually, it's almost impossible to do anything at all with that, right? Because the ambient light is so strong. So, but yet our algorithm actually works pretty robustly, even outside. And these are some preliminary results that will be presented at SIGGRAPH later this year. So just to give you a sense of, the topics that we're working on in my lab, I'm the director of the computational imaging lab, and we actually work on augmented and virtual reality, especially on the optics and head-mounted displays, work on light field cameras, computational microscopy, and a couple of other topics. I only showed you some of the recent work that we published on time-of-flight imaging. I'd like to thank my group, especially Matthew O'Toole and David Lindell, who've been doing most of the work that I showed you today. And with that, I'd be happy to take any questions that you may have.
Yeah, thanks for that really interesting talk, Gordon. One question I had is you mentioned that it's easier to work with certain materials than others. Do you have to train the algorithms differently for the different materials, or do they work across all material classes, and it's just that the results are better for some classes of materials than others?
Yeah, so the amount of light you get back from certain materials is just higher than for other materials. So if you drive at night, a lot of the strips on the street or the traffic signs or safety apparel, those use a lot of retroreflective materials simply for the normal driver to, be able to make them out in a more easy way, because simply the amount of light that's returned is like orders of magnitude higher than for regular objects and regular materials. And the same concept also applies to non-line-of-sight imaging. If you have a retroreflective object hidden around the line of sight, you could detect that more easily simply because you have a higher photon count. So our algorithms are pretty agnostic to that. We do have to have a rough idea of what the material is or what the reflectance is, but it's pretty robust to slight changes in the material. For the closed form inverse solution for the looking around corners project. For the neural network for direct reflections, we train it actually on multiple different reflectivity levels all at the same time. So in that case, you're only going to look at how many photons are actually returned back to the source. So the more you get, the more the photon count, the better it is, of course. The lower it is, but that's where the challenge is. So algorithms and systems today work pretty well if you get a lot of photons back. But the big challenges are at these low photon counts when you get 1 photon per measurement, or less, actually, on average, right? That means you shoot 1,000 pulses into the scene, but only one of them actually triggers an event. So how do you make any kind of decisions then? But that's really what's the key of pushing the range and resolution and density of these types of detectors.
Great, and let me ask actually, since I have the microphone, another short question is, how do you measure quality of the results? It's pretty clear by just looking. So we've applying our own visual systems, and we can score them in some informal way. But how do you like quantify quality of results in a more quantitative way?
I mean, that's an excellent question, right? So we typically have a couple of setups in the lab where we put a planar surface on a translation stage, for example. We know what the ground truth depth is. We move it to multiple different depths, and we know the ground truth. We plot the estimated depth against that. We have 3D resolution charts also to be able to determine the spatial and axial resolution of these estimation methods. And then, of course, we can always use simulations to extensively simulate data under varying conditions and also compare it to other methods. So it's oftentimes not practical to implement somebody else's method on your own system. Sometimes the code isn't available and so on, but oftentimes the authors are willing to share their results, and you can compare it in simulation. So there's many different ways of how you can, validate the accuracy of these systems, but it's absolutely critical. Yeah.
Hello, Gordon. This is Juan from CloudMinds. Amazing work over here. My question had to do with your last project, the one where you're trying to build 3D maps based on your photons. My question has to do with how thin can the object that you're trying to reconstruct be? Can it be as thin as, a sheet of paper? Would it have to be thicker in order for the algorithm to reconstruct it correctly? Okay,
so you're asking how thick does an object have to be for the direct 3D imaging or for the non-line-of-sight imaging?
For the direct.
Direct imaging. It actually doesn't matter that much how thick it is, or do you mean how small can they be?
How thin?
Thin doesn't matter as long as they reflect photons back to where it came from. It's completely agnostic to the thickness. right? I mean, there are some challenges. If you think about foliage, right, that's a challenging case. You have many small objects that are very thin all together, right? So the projected laser spot will have a certain size given by the diffraction limit, actually, right? So if within the laser spot there are like 10 different leaves or so, like it's not entirely clear which depth you get. So those are the challenging cases, and so the thickness of the object can have an effect on the precision, but overall, as long as features that are bigger than the projected laser spot in the scene will be reasonably well resolved, as long as photons come back, or at least one.
Awesome, thank you.